In this video, we will take a closer look at staggered adoption designs. In the last video, we've already seen that staggered adoption designs can be quite tricky. Actually, in most cases, are very tricky to interpret. The reason is that they are based on a two-way fixed effect model, and by construction, that statistical model is a weighted average over many different things. So you have several ingredients that go into this estimator. One it's a weighted average of various 2x2 group comparisons. So you compare early adopters to late adopters to early adopters, non-adopters to early adopters, non-adopters to late adopters, and so on. And what's more is that each of those 2x2 comparison groups enters the estimator with a weight. And those weights depend on many factors, especially they depend on the variance in treatment within each group. And as such, they can be quite tricky to interpret, and you get results that are very far away from the parameter you actually want to estimate. So most people, when they use a staggered adoption design, they interpret the results as if they were estimating an average treatment effect on the treated. So they say this is the effect of the treatment for a given state, and that obviously implies that there is a counterfactual that tells us what that state would have had, what outcomes that state would have had it not been treated. But interpreting that, interpreting different diffs with two-way fixed effects in that way, this is what the Bacon decomposition shows us, is actually not that straightforward. So in this video, we want to take a closer look at the gap between what it is that you're estimating and what would be policy relevant parameters that you actually want to estimate. And then we can think about, well, under what conditions do the two of them coincide and when do they not coincide? So in order to do that, let's first look at different parameters that we might be interested in, or that form building blocks at least of parameters that we are interested in or that we can identify. So let's start with this average treatment effect on the treated for a timing group K. So timing group K is all the units that are treated at the same time, right? That's what we refer to as a timing group. And then at point T, the average treatment effect for that group is simply the outcome that we observe now that it has been treated in that given period. So the unit may have been treated, let's say, in 1990, but we actually want to know what is the treatment effect in 1995. And so the average treatment effect on the treated for the 1990 treated group in 1995 is the outcome we see in 1995 versus the counterfactual outcome we would see in 1995 if it wasn't for the treatment. We can also do the same thing for a whole time window, whereby we say we look at the averages across different or within the same time window, right? So we have the observed average outcome in a given time window between 1990 and 1995 under the current state where the unit has been treated, and then we look at the average outcome in the same time in the counterfactual state where the unit has not been treated. And another building block that we should consider here is the difference over time in average potential outcomes. Okay, so if you look at different time horizons, then within each treatment status, you obviously can also have a change in potential outcomes. Okay, if there's, for example, a time trend. So that's what we see here. We see here two potential outcomes and how they move over time. And when I say time period and average across time period, what we do very often in difference estimation, and what will be very important for analyzing the effects that we get from a two-way fixed effect estimator through the lens of that Bacon decomposition, is simply to think about the comparison between a state after and a state before, right? And so obviously there is a time trend in that, but we compare the average before to the average after, right? And so the before-after comparison on the treatment is what you see here, the difference between the two red bars, and under the counterfactual would be the difference, the equivalent difference on the line of Y naught. Okay, now what we should look at then a little bit closer is, well, to what extent can we actually look at the average treatment effect on the treated with our fixed effect estimator, and what is it then that we have to assume, and what do we actually know about the parallel trends assumption, right? Because in a 2x2 estimator, you have this formula up there that tells you exactly if the parallel trends, if the time trends in outcomes are parallel. So in absence of the treatment group would have moved in exactly the same way as the control group did. Then our estimator identifies the average treatment effect on the treated. But when you have many such 2x2 pairs, then the question comes, well, you know, how can we make sure that parallel trends are actually given, and do we actually have to assume that, or what do we have to assume that in order to identify the average treatment effect that we want to identify? And so that's these are all building blocks of what is to follow here. So you can see here once again, you have basically a group that is the that is untreated. That's the one at the bottom, and then you have a group that is the untreated group is actually the one that you see up here. And then we are actually interested in the treatment effect on the treated group that gets treated at this point. And here, the idea is that we have here that the counterfactual for the treated group is constructed based on the movement of the untreated group. Why am I showing you this? I'm showing you this because this is important for thinking about what, again, the 2x2 model identifies, and how we should think about those 2x2 models whereby we have these early versus late comparisons. Okay? So if we have a model where the late adopters are a counterfactual for the early adopters, that's a fairly straightforward case. Because here what we compare basically is the average treatment effect on the treated in the middle of the sample period to the parallel trends in the first and in the middle period. So what do we mean by that? Let me quickly draw this. So you have here your different sample periods. So you have an early adopter that moves like this, then their outcome jumps like that. And then you have a late adopter. Let's draw them in green. And then their outcome jumps the same way a little bit later. Okay? So here in the late period up here, both are treated. So that there is no variation in treatment anymore. So the estimator doesn't put any weight on that period. Okay, so the estimator only puts weight on periods where either both are 0, that's the pre-period here, or where 1 is 0 and 1 is 1, which is the period in the middle. Okay, so let's call this 1, 2, and 3. And now, or here we call them mid and pre. And now very clearly, the average treatment effect on the treated is simply the difference between this red bar and that red bar. Okay, and so we take the average before and the average after, and obviously take the same difference for the control group, which is this orange bar and that orange bar, and let's call the difference between the orange, let's call it B, and let's call the difference between the red, let's call this A. Then our average treatment effect on the treated is nothing more than A minus B here. And that's the 2x2 difference in difference in that pair, right? And obviously in that pair you could also have a parallel trends bias, because, well, trends may not be parallel. Okay, so obviously if the blue and the green are on a different time trend, then the green is not a suitable counterfactual for the blue. So what that tells us is, in this time where we make that comparison, we need to have parallel trends within that pair for our research design to identify the average treatment effect on the treated. But now come the late versus early pairs, and that's where things get really interesting, because that's nothing more than what we are used to from 2x2 different diffs. It's 2x2 different diff is average treatment effect on a treated plus the bias that comes from non-parallel trends. But here we are in a very different game, because we have the average treatment effect on the treated, we have a parallel trends bias, and we have what's called a heterogeneity in time bias. And that's new. That you may not have heard before, but I will show you in the next couple of slides what is meant by that. And in a nutshell, what is meant by that is that the early adopters are a control group for the late adopters, but there is a problem if the treatment pushes the early adopters on a different time trend. Because if they no longer follow the same time trend, then they're not a suitable counterfactual anymore. So it's important here to distinguish two different types of heterogeneous treatment effects. I mean, these days when you read methods papers, kind of the current research frontier is to think about how to deal with heterogeneous treatment effects. So how to interpret estimates, and also how to identify policy relevant parameters if you have selection into treatment, or if treatment effects change over time, or both. So here we have heterogeneous effects across groups. What do we mean by that? It means that across those different groups that are defined by their treatment timing, early versus late versus never adopters, the treatment effects differ. So for example, if an early adopter gets treated, maybe the treatment is more effective there than if a late adopter gets treated. And maybe the treatment is also more effective in a late adopter than in a never adopter. So there may be a reason why some states never adopt a treatment. That's heterogeneous treatment effects across units or across groups. There is also another type of heterogeneity that comes into play here, especially when we look at those late versus early comparisons, and that is heterogeneous effects within a group over time. In other words, it's called a different time trend. Right? So one example you can see here. Okay, so here you see an early and a late adopter. And again, we're looking at this comparison where the early adopter is a control group for the late adopter. And now what you can see what happens, instead of a level shift as we had it in the previous examples, here now we have a shift in trend. We have a kink point, right? So initially they're both on that red path here, but then you have all of a sudden this differential trend where the treatment affects the path over time. And that's what we mean by heterogeneous effects within units over time. If I take for the early adopters the treatment effect of early versus middle versus pre is smaller than when I take late versus pre. So if I call those time periods again, 1, 2, and 3, if I take the difference in outcomes for the red line between 2 and 1, that's smaller than between 3 and 1. That's what we mean by heterogeneous effects over time. And now obviously they could also be non-linear, they could revert back at some point, but the fact of the matter is that it's not just a level shift. That's what we mean here. And what is the problem here? Well, the problem is that now the first period is not actually the one where we have where our estimator puts any weight. So that we can basically cancel. All we care about is, again, the red line being a counterfactual for the black line. Right? Now see what happens here. You have a before period that's here, that's the pre-period, and that's the post-period. Okay? But what we typically do is we would say, well, you know, the correct counterfactual path for the late adopter would actually be that orange line here. Okay, that's the correct counterfactual path if parallel trends hold and such. Okay? But we are not using that as a counterfactual path. We are using the red line as the counterfactual path. And that's problematic. So let's think again about what the difference in difference estimator, whereby the early group is a control for the late group, what that difference in difference estimator actually identifies and what it should identify. It should identify, I'm gonna draw that in green. It should identify the difference in the controls. So let's call this A, and let's draw in another color, in blue, the average outcome here versus the average outcome there, which coincides, and let's call this B. Okay. So now what the difference in difference estimator is simply B minus A. That's the correct difference in difference estimator. Or that would be the correct difference in difference estimator. But now look what happens if you have, if the earlier unit, the early adopter, is pushed onto a different trend. The counterfactual is very different, right? The counterfactual in the correct one would be A. In the incorrect one, it's not A. So let me just remove those. And let's think what the correct counterfactual would be here. Well, okay, so first of all, B remains as it is. So B is the difference between the observed average after of the treated group and the observed average before of the treated group. And so B remains. So let's call this correct. Diff in diff would have been the one I've drawn and since erased, but on the video you can obviously go back and see what it's like. It would just make the whole thing too messy looking. But now we still have B remains the same, but now the counterfactual is very different because we take the difference between pre and post in the red line as the counterfactual. Okay? So here we take, let's do this in light green, we take the difference here versus the difference there. Okay, so that, let's call this A prime. Okay, so in other words, the biased diff and diff estimator is B minus A prime. Right? And very clearly, A prime here is greater than the initial A, which was just that difference here. So we will get an underestimate. So the estimate that we're getting is smaller, and not in absolute value. It's smaller, and it could even be negative. So even if the true effect B minus A is positive, it could be that B minus A prime actually turns out to be negative. Now, is this a problem in practice? Well, it depends, right? So you have maybe situations where it's fine, that creates a lower bound and the true value might even be higher than what you're estimating. That's fine. But in other cases, it could be very far away from the actual politically interesting parameter. And so therefore, it's obviously important. We want to go after the gold standard, which is the average treatment effect on the treated, and any bias that we introduce here, in practice, we may not be able to avoid it, but we want to minimize it. Right? And so those early versus late comparisons have this problem. Okay, so in those cases, when the earlier group is a control group for the late group and is pushed on a different trend, you don't have the correct counterfactual. For the other three groups, it doesn't matter. The counterfactual is the intuitive one. Okay, so you have to be aware of this problem that comes when you have heterogeneous effects within groups over time. Those are the real problems. That does not mean that if you don't have those, that it's easy to interpret a different diff estimator. Why? Well, you can see this again here because you just have a lot of different ingredients that go into this one parameter. Okay, so here you have again all the weights and all the 2x2 pairs that go into the estimator. And this could obviously be more than 3 groups in the middle, because if you have the typical staggered rollout across 20 states over many years, you have potentially lots and lots of different groups whereby you compare late to early and early to late. Now, then comes the question, well, what parameter, if we have all those weights, what parameter are we actually estimating? And this is the second big achievement in Goodman-Bacon's paper, is that he actually expresses this beta diff in diff, that parameter, and that weighted average that underlies that, in terms of the standard diff in diff parameters and bias terms that we're getting. Okay? So the first one is equivalent to the average treatment effect, or is similar to the average treatment effect on the treated, with one difference, and that's that VW, which stands for variance weighted. And it's variance weighted because you have a fixed effect estimator, and then by construction, the estimate you're getting is a weighted average over all the individual treatment effects of each unit, weighted by the actual variance in treatment within each group. And then groups with a higher variance get a higher weight. But that we may be able to live with. Depends also, how much the variance varies across groups. But given that we typically have only a limited sample period and we have some that are adopting very early, some adopting very late, and some in the middle, it's inevitable that those who adopt in the middle get a much higher weight. That's just in the nature of the research design and the statistical model that we are using here. Then we have a second term, and that is equivalent to, or is similar to the common trends assumption, but we don't have the common trend in one 2x2 pair, but we have a variance weighted common trend. So it's basically an average common trend, again weighted by the variances within groups. So the variance in treatment within those 2x2 groups. And then we have the third term, which is the term that reflects this problem here. And so the fact that treatment effects within a group change over time. And then very clearly, if we want to identify the variance-weighted average treatment effect, we need to assume and also then justify why these other terms are zero. So why is it that the treatment doesn't push units onto a different time trend? That's an assumption that we need to justify. In some cases, they may be justified. In other cases, it may simply not be, but it cannot directly be tested. So it's not enough to, as people do, then just throw in some state-specific time trends and hope for the best. That's not how it works. Right? So because it's an identification assumption, it cannot be tested. You can bring maybe some evidence based on pre-trends or based on placebo outcomes, maybe. But Goodman-Bacon actually in his paper proposes some diagnostic tests based on covariates. So I strongly recommend if you plan on using a diff in diff to look at that method. Okay? So we need to assume that. And we need to assume that these common trends on average are also zero. And in the best of cases, we can then only identify the variance-weighted average treatment effect on the treated. And that is not a very interesting policy parameter, I would argue, because again, those units that choose the treatment very early or choose it very late get a very low weight in this. And the weights also then depend on the gaps basically between how much time passes between the treatment of two groups that eventually get treated and so on. So in other words, we can get a weird average treatment effect on the treated that is not very policy relevant in the best of cases. Let's have a quick look at that second, first of all, at the variance-weighted average treatment effect on the treated. So obviously, if for each group, the average treatment effects are the same for all groups, then the variances don't play a role here, because a weighted average over all the same values is just that same value. But in any other case, you have to understand those variances, and those variances lead to very odd combinations of weights. Then we can also look at the common trends assumption, and here's something interesting, which is, note here that the variance-weighted common trends is what it says. It takes the common trends, the parallel trends, from each 2x2 pair and weights them based on those variances and also those weights that depend on the difference in in time periods, how many time periods are basically the late versus the early adopters, how many time periods they're treated. So what we need in order to identify the variance weighted average treatment effect on the treated is we need that this sum is 0. So it doesn't mean that we need every single pair to have parallel trends. It's just that the trends on average, but the weighted average of those trends has to be 0. To what extent one can really defend that is actually a tricky question. And again, there are some diagnostics tests one can do based on placebos or based on covariates, but it's definitely not easy, right? Because you need to assume, in order to identify the effect you would want, you need to assume that sum is 0. This is also a very neat way of putting the weights and thinking really about those weights that go both into the average treatment effect on the treated as well as the variance weighted common trends. And so here what you have is, for two types of setups, the weights of each observation and to what extent those weights, that observation is more likely to show up in a treated group or in a control group. And you see that that's hump shaped. So let's look first at those two designs. The first is one, the gray line up here is one where you have actually some units that have never been treated. So you have some real control group. Whereas the second line, the dashed one, is one where you have a setup where everyone gets treated eventually, just at different times. And what you can see here is that those, and on the horizontal axis, you have basically when over the event window, at what point they are getting treated. And so those that are getting treated in the middle, they have a much stronger weight in the treatment group in both the estimation of the average treatment effect on a treated, but also in that bias term. And the others, so those at the margin that get treated either at the start or at the end, or towards the start and towards the end, have a much stronger weight in the control group, both in the average treatment effect on the treated as well as in that bias term. And that's not something that's desirable, because I will show you an example in a couple of slides where you can see that in a study that is very well published, that the result that you're getting is actually just the result of a couple of these 2x2 comparisons that have very strong positive weights in the treatment group. But let's look first at the third term. So remember, the different diff estimator is the variance weighted average treatment effect on the treated plus the bias term from common trends plus the bias term from basically the treatment pushing treated units onto a different trend. Okay, and so here there is this is obviously also some sort of average, but it's a lot easier to understand, right? It just means that we want to that on average the treatment should only lead to a level shift but not a shift in trend. Okay, and this is obviously only driven by those comparisons whereby the early group is a control group for the late adopters. Now this may all sound pretty abstract, right? Now, conclusion from that is it's complicated. Diff in diff is not as easy as one may think and as lots of researchers make you believe. So then let's look here at an example, because one may say, well, there's always a bias. In econometrics, you can never get an unbiased estimate in practice. So what's all this problem about? Well, again, here, let's see how the sausage is made. Okay, let's take a well-published study, in this case from the QJE, that's taken actually from Goodman-Bacon's paper, and that uses that methodology, and let's see where, what those weights do in that study. This is not to say that these authors did anything wrong here, not at all. This is a very well crafted study. It's also, it's been 15 years ago, and at that time, no one really even thought about those problems profoundly. But it's a very good case to study. So Stevenson and Wolfers studied the effect of divorce laws in the US on suicides among women. So the idea is that if you have unilateral divorce laws, if women can simply divorce their husbands, they are not trapped in, or they're less likely to be trapped in abusive relationships, and that may also then reduce the likelihood of them committing suicide, right? So the dismal science likes to study these type of questions. And now here you can see the result from the main result from Stevenson and Wolfers, which is that so they basically do an event study first of all, but then they also summarize it with a simpler parametric different diff, but two-way fixed effect model really. And you can see here that, so you had a staggered rollout. Some states started that process pretty early in the 70s, and other states followed suit until the 80s, but then there was also some states that never introduced unilateral divorce laws. And you can see that there are parallel pre-trends. Again, how do we interpret them? It's actually not so easy. But then after a state is treated, there is a disproportionate decrease in suicide rates, and that's also statistically significant. Now, if you just summarize this by one coefficient, we would have minus 3. Right? So I think this means that if a state introduces that, then per year relative to control states, you would have 3 fewer suicides per 1 million women, which is probably not a small effect, given, thankfully the number of suicides not being that high to begin with. But let's see now, let's do the decomposition. Okay, and so I'm taking this all from Goodman-Bacon's paper, and let's see what he finds there. So what you see here is each of those dots is one 2x2 pair. Now here you have lots of 2x2 pairs because you have the early adopters, the late adopters. You have 37 states that implement this reform over the period of over 20 years. Okay, so you have lots and lots of comparisons, and then you have comparison early versus late versus early, and so on. And so on the vertical axis, you see the difference in difference estimate for that group. And then on the horizontal axis, you see the weight of this particular group. And so you can see here that, first of all, when you look at the support just purely on the vertical axis, you see that within each of those groups, these different diffs, when you compare them, they vary wildly from minus 30 in some cases to plus 30. Right? They vary. Right? And then you see that there is only a small group of that you can see around here that actually have any meaningful weight in that estimator. Okay, and then you can also see which are the states. So this is so there is one group, you'd have to read the exact paper, but there is one group with treatment effects of about -7, and then you have another group of treated states versus non-reform states where the effect is -5, but then you also have some with a positive weight that is also not that small, where the effect is actually positive. Right? And so here the estimate you're getting is even though you consider all states and you say, oh, this is, in the average state, if they introduce unilateral divorce, then suicide rates go down on average. But that average is a strange weighted average, and the strangeness of all that we see here, right? Ideally, you would want them all, you wouldn't want to see any dispersion here, right? So you want to see an equal weight for each of those dots and the same effect. That's what you would ideally want to see, right? And here you can see that it wildly varies. That obviously means that the difference in difference estimations that we do may actually reflect something completely different from what we are claiming that they're doing. So the lesson from that, from the Goodman-Bacon paper predominantly, but also from other papers that I reference, that have shown something similar and highlight maybe a different aspect and extend that idea to other types of estimations, for example, to flexible diff models. The big conclusion here, it's complicated. Right? So if you look at it, for a while people were very, very critical of instrumental variables estimators because it's so hard to defend the identification assumptions, and diff in diff was always considered as much easier. All you need is the parallel trends assumption and you're done. But then the question comes, so what are you actually estimating? And the answer is, it's far from trivial to say that. Right? So there's actually more research needed and newer methods needed to solve this problem. With the common estimators, we cannot solve that problem at all. Okay? And another thing that is very important here that goes for diff in diff studies as well as any other study that uses a fixed effect estimator. Fixed effects may be important for isolating variation along certain dimensions, but they also come with the problem of the estimator being a variance weighted estimator. Right? So your estimator is inevitably a weighted average, and those variances, the variance in treatment within groups may lead to an estimate then that does not reflect the actual policy relevant effect that you're actually interested in. So what can we do? What can we do better? Well, first of all, we can use Goodman-Bacon's method and simply graph the 2x2 pairs and graph the weights and see, are those weights very close together or are they all over the place? If they are all over the place, it probably means that what we are estimating here does not correspond to an interesting parameter from a policy perspective. And also we need to obviously corroborate the assumption of common trends as well as the one of heterogeneous effects within groups over time, of homogeneous effects within groups over time, as in level shifts as opposed to changes in trends. We need to justify that through additional evidence. That can be a bit hard. Okay? And one thing we can obviously do is we can use a different estimator altogether. And this is really where the research frontier currently is. Basically, what people are trying to do now is to circumvent this problem that the earlier treated groups are a control group for the later treated groups, because this is the group that really messes things up. There is also the idea of undoing those variance weights in various papers. And so you know, if we know what those variance weights are, we might actually be able to undo that bias to some extent and simply recover. It's not really a bias, it's just we may actually undo those weights and uncover the average treatment effect on the treated, but it's not easy. So here is where a very new paper is coming in, and I'm just gonna sketch the idea of the paper here. That's by Caraway and Santana, and especially Santana is one of the authors who has written extremely insightful diff papers in the last 2 or 3 years, and will definitely be one of the very influential people in this literature for many years to come. So their idea is as follows, that their estimator is basically the combination of separate estimations of different average treatment effects on a treated for different groups. What do we mean by that? So suppose you have a staggered adoption design. So again, some groups never adopt the treatment and some adopt early, some adopt a little bit later, some adopt very late. Then what the average treatment effect on the treated for one particular group is, it always only considers the effect for that group versus any group that has not been treated yet. So if I'm the group that is treated first, then my only control group that I consider are those that have not been treated. Right, so if I'm treated first, I'm comparing myself to everyone else, right? Because I can compare myself to those groups that have not been treated at all, or to those groups that have been treated very late, and I compare myself to those until they're treated as well. And so this is done for every group except for the very last one, which may not have an actual comparison group here. And so the very last group that adopts can only be compared to the group that has never adopted, or will only at some point in the future, but beyond our sample period, right? Whereas the group that adopts first can be compared to the never adopter, as well as to all groups that adopt at some point at a later stage. And so what they do is, for each adoption group, for each cohort they call it, they compute the average treatment effect on the treated, and then they form a weighted average of those average treatment effects on the treated. What that gives us is, it excludes this nasty comparison of late versus early adopters, because you always only compare a group that has already adopted, that's the treated group, to groups that have not yet or never adopted. So if you have a scenario where your identification only rests on timing, where all get treated, that excludes then the very last group, because for that you never have a comparison group. Whereas if you have a group that never gets treated, then for each treated group you always have at least one, if not more, comparison groups. So what that does in practice, and what that is based on, is the following. So here, what we first need to think about is the so-called group time average treatment effect on the treated. Okay, so that's the average treatment effect for a given group, and with group we mean all units that have been treated at a given point in time. And then we look at that average treatment effect at some point later. So again, suppose the group was treated in 1990. We want to know what is that group's average treatment effect in 1993. But in doing so, we need to compare that group's average outcome that we observe, which is that, to some counterfactual. And what Callaway and Santana propose here, and what I will not go into great detail in here, you need to read the paper to exactly see what they're doing here, is to say, construct an estimator for that group time average treatment effect on the treated. So what is that estimator? It takes simply the outcome or the average outcome of the treated group versus the average outcome of the not yet treated groups and weights them with this weighting function. That weighting function is a little bit hard to swallow, but what it does is basically those units that in terms of observable characteristics are very similar to the treated unit, they get a very high weight here, and similarity here is determined based on a propensity score. Whereas those groups that are very dissimilar in terms of observational characteristics receive a low weight in that estimator. Okay, and that then, so basically what it does is based on a propensity score and based on the time trends of all the not yet treated outcomes, it constructs a counterfactual for the treated outcomes. Okay, so we have then for the group that has been treated in 1990, we then construct the counterfactual time trend for all units that have not been treated even after 1990. Okay, so if I want to know what is the average effect, average treatment effect for the group that was treated in 1990, but I want to know what their average treatment effect is in 1993, then I take all the groups that have not been treated until 1993 and use those weights then to construct among all those trends and outcomes of all those groups that have not yet been treated in 1993 to have one that is as similar to the treated group as possible in terms of observable characteristics. So this is somewhat similar in spirit to what the synthetic control method does. It's not computationally it's different, but the logic is actually not too dissimilar to a synthetic control estimator. So we do this for all the cohorts, okay? And then we take this average treatment effect on the treated for all the cohorts and all the times to the extent that we can, to the extent that we have comparison groups left, and then simply average across all of them. And through these averages, we can recover, and that's what they show in the paper, some very interesting policy relevant parameters, and we get around this inbuilt problem of those late versus early comparisons. So basically, the two-way fixed effect model gives us a statistical straitjacket that we find it hard to actually deal with and hard to liberate ourselves from. And that paper, as well as others in that literature, give us one way of doing this. And if you want to do a definitive study, does it mean you have to do all these different things? Probably not. But you have to at least be aware of them and then pick the ones that are useful and make sense for whatever your study is trying to achieve. So bottom line for diff in diff studies, to wrap up this entire lecture. It is often seen as a transparent research design, but I guess I could convince you that unless you are in the 2x2 simple world, it's not a transparent research design at all. There are so many potential sources of bias, and even if there is no bias, then still interpreting the results is really, really difficult because of those strange weighted averages. But thankfully, we have also new methods that help us overcome those problems. So I'm citing here quite some of the papers. This is by no means an exhaustive list, but it's a start, and it's very important to stay up to date on those methods if you want to use diff and diff in your own work. And I hope, despite all those potential pitfalls, that you will do so, because it is a method that is very, very powerful and can create many, many important insights.